Alright, so in this video I'm going to be explaining an important article with the title Taxonomy-structured domain adaptation. This article in 2023. Domain adaptation aims to mitigate distribution shifts among different domains. However, traditional formulations are mostly limited to categorical domains, greatly simplifying nuanced domain relationships in the real world. In this work, we tackle a generalization with taxonomy-structured domains, which formalizes domains with nested hierarchical similarity structures, such as animal species and product catalogs. We build on the classic adversarial framework and introduce a novel taxonomist which competes with the adversarial discriminator to preserve the taxonomy information. The equilibrium recovers the classic adversarial domain adaptation solution if given a non-informative domain taxonomy, for example, a flat taxonomy where all leaf nodes connect to the root node, while yielding non-trivial results with other taxonomies. To this end, we extend domain adaptation to taxonomy-structured domains. Taxonomies abound in our culture for categorizing items, ranging from biological studies to library classification systems. Mathematically, taxonomy is just a nested hierarchical representation, and each node in the taxonomy specifies a level of invariance that holds for the domain within the node, which can be further broken down to a lower level of invariance in its child nodes. Finally, the lowest level of invariance is simply a single domain. So the lowest level could be a single domain. We emphasize that a taxonomy of domains is different from a tree of domains, as a non-leaf node in a taxonomy typically involves multiple domains. For example, this one is non-leaf. It has multiple domains. The specification of invariance among domains thus becomes nested, which can be naturally translated to the induced similarities. Indeed, the similarity between the two domains can be easily gauged through their common ancestors, which are also nested. In domain adaptation, an input, for example, a bird image, is used in conjunction with additional domain specification to predict a label. For example, the color of the wing. Now we consider an unsupervised domain adaptation with n domains. And in this work, we assume an additional taxonomy. We have this one that specifies a hierarchical similarity structure over the domain. Formally, taxonomy can be represented as a tree. So the root node U, in each layer we have parent. In each layer, a parent is split into disjoint children nodes, and each leaf only contains one domain. So the final things these leaves are just one domain. But the non-leaves like this has many domains. So you get the idea. We emphasize that a taxonomy of domains is different from a tree of domains. A non-leaf, as I said, is a taxonomy, does not correspond to a single domain. So this is the difference between typical domain adaptation. In typical domain adaptation, you just have a discriminator. For example, you design the encoder to fool the discriminator, but in this paper, we have not only discriminator, but also your taxonomy. because it classifies the domain index, this one or this one or this one. Not only classifies the class of that, but also the domain index. And reconstructs domain taxonomy given encodings of data from different domains. So we assume an additional taxonomy. We have an encoder. Encoder E leverages all the available information to build representation E sub L. It takes as input the data X sub L, domain index U sub L, and the distance matrix A. To facilitate learning, we first leverage an intermediate domain embedding. So this is an intermediate domain embedding, Z, to capture the immediate dependency between U sub L and A. Remember that we transform the taxonomy to a distance matrix. So AI sub J records the shortest distance between two domains I and J in the taxonomy, for example. For example, what is the distance between this one and this one? That is encoded with the entry A sub J in the matrix A. So different domains, what is the distance between them? It's like a graph structure in graph neural networks, very similar, like the adjacency matrix that we used to talk in GNN. So in principle, given sufficiently powerful F, every embedding works equally well as long as the bijection to a set of domains can be formed. Here we use a simple pre-training procedure to obtain the domain embedding based on a reconstruction loss with respect to domain distance matrix. The discriminator aims to identify the domain from the encoding E sub L. This is realized as a function D that minimizes the domain identification loss, where expectation is taken over data distribution. L sub D is just a cross entropy. Now, let's focus on this taxonomist. Similar to discriminator D, the taxonomist aims to recover taxonomy information within the encoding E sub L. Unlike the vanilla categorical domain index that can be easily compared element-wisely, the distance matrix is implied by the taxonomy is pairwise in nature. We therefore specify the taxonomy with paired inputs and optimizes it with respect to the distance matrix, where the expectation is taken over a pair of IID samples from the joint data distribution. Here L sub T denotes a regression loss. The predictor F simply takes encoding E sub L as input and outputs a label. We therefore optimize it with respect to the labels. So this expectation is taken over only the data in the source domain. S stands for source. Because labels are not available in the target domain. So this is the full game. We want to design the encoder to fool the discriminator. Similarly, we have two more terms because first we have taxonomy and also we have F that I will explain. So E, F, and T play cooperatively against the discriminator. So this is the discriminator, and then we have encoder, we have F, and we have T. So these are against what? These are against the discriminator. It's a game. So we solve this min-max problem to get the appropriate discriminator E, F, and T. Traditional adversarial domain adaptation enforces encoder to full discriminators so that it aligns domain uniformly. In our model, due to addition of taxonomies, the encoder has to return a certain amount of domain information in order to recover taxonomy A, such that the alignment is no longer uniform. As a result, the discriminator must compete with taxonomies during optimization process to reach an optimal balance. So we formally show that the proposed formulation indeed allows the model to achieve a balance between the two contrastive goals, removing domain information and preserving domain structure. We focus on the analysis of encoder, which is the direct subject of regularization. Following prior literature, we say that domain information is fully removed or the domains are uniformly aligned, which means the encoding distribution of every domain are aligned as defined below. So the definition of uniform alignment is that a domain adaptation model achieves uniform alignment if the encoder satisfies this probability. On the other hand, the taxonomy information is fully retained if the loss between T and E taxonomy and the encoder is zero. The domain taxonomy can be perfectly reconstructed from the encoder. And then we have a definition of non-informative domain taxonomy. A domain taxonomy is non-informative if and only if the entry of a matrix is A for some constant A. And then we have a theorem, incompatibility. If E and U are orthogonal and L2 distance is used, then the loss between taxonomy and encoder is zero. Then we can say that it is constant for some constant A. And then, so you see the domain taxonomy of ImageNet attribution. For example, this one has many domains, but the leaves like this one, and this one has just one domain. Uniform alignment. So if lambda sub t and domain taxonomy is not non-informative, then the min-max will not yield uniform alignment. To model the pairwise distance introduced by domain taxonomy, a straightforward way is to utilize a weighting function which captures the distance for each pair of domains. For example, the weight could be inversely proportional to the domain distance, this way, and we can then adapt dA and N by utilizing a distinct discriminator. So you see the domain taxonomy with 18 domains shown as leaf nodes. Note that the leaf nodes are marked with black base and white text. And this is a detailed result with 14 domains. You see the accuracy is 31%, but for different, and now here is 54. The spectrum from orange to yellow indicates accuracy. For example, for this domain, the accuracy is higher than for example, this domain.